My name is Tom Yacobelis. This is Air Quality Control COVID Clean. These are airflow concepts designed to lower occupant risk. Jeff Peters from Rimkus and myself are presenting this today. And our bios are there in case you care to read them. Say hello, Jeff.
Good morning.
So when we have a live contaminated space, I was just saying that the Harvard and MIT tools that they have developed determining how long someone can be in a space, it's all based on having a single live contaminated person or an asymptomatic person in that space. And we can actually measure nowadays what the rate of infection might be or contamination might be inside that space, depending on what precautions have taken in that space. Some stuff that you find very interesting, actually, which we'll talk about today. So we want to talk about it, especially in your area of the country. We have some dynamics that are really kind of unique. One of them is that we have radiated heat, we have passive heat, we have some systems have furnaces, some systems have large mechanical systems in it. And when the children or when the students are inside the school environment, if the windows are closed on the inside of the environment, we get a particle buildup. The dynamics of airflow are such that there's a particle buildup inside that building that we want to try to control. And I know that this has been discussed quite a bit with respect to HEPA air scrubbers and opening windows and whatnot. But we want to point out some of the issues that you might encounter that you might not have considered, especially when we're talking about opening windows. Now, in the classrooms or in the environments inside the school that have either a recirculating system or a furnace, generally what happens in these areas is that the mechanical systems have filtration inside them that can be upgraded, so that when the filtration is pulling back air from the room and it's filtering it through the furnace itself, a higher level of filtration will pick up more particles in the environment. These systems are designed to run around if the fan is left in the on position on the furnace, which is not a normal thing for furnaces or air conditioning systems to have. But there's a little switch on the air conditioning systems that allow furnaces to be run in a continuous fashion. When you turn on the blower or the furnace in a continuous fashion, you are then scrubbing the air continually inside that environment. So the first thing we want to talk about is leaving these systems on, converting any air conditioning system or furnace to a clean air machine, essentially, by upgrading the filtration. And we know you've considered some of that. But also we want to also start to learn a little bit about the gross particulate matter that is usually engineered to come into the air conditioning system as well. So one of the fundamental takeaways we want you to understand today is, depending on what the particle matter is outside the building, if you open a window or you're pulling it in through an air conditioning system, if the particle matter is high on the outside, bringing fresh air into this system, you really have to filter it in some way. Otherwise, you can be increasing particles to the indoor environment. The other thing that we're concerned about is in those classrooms that do have ventilation systems with air conditioning systems, sometimes, depending on where the students are sitting, if the airflow is flowing in one continuous manner, and I'll explain this in a minute by looking at some of the air conditioning registers that we have out there. The airflow is flowing from one side of the room to the other side of the room. This could be problematic too, with the spread of a asymptomatic COVID person to non-asymptomatic people. Now, of course, if they're all wearing respirators, this has a profound effect on the reduction. It really, really reduces the risk quite a bit if everyone's wearing the respirators. And the type of respirators are very important as well. There's a big difference between some of these respirators that are out there. However, even though you would think that most of the time air is moving through a room like this, when it comes to the particles are the inside of the environment. They really go everywhere. As soon as particles enter to the environment, they basically distribute themselves throughout the entire environment. So in many cases, if we're bringing in outside air through a window, as soon as high particles come into the indoor environment, we have high particles that we want to remove from that indoor environment as well. Now, in a number of classrooms, there is no furnace. There is just heat inside the rooms themselves. And so we're dealing with a condition of how do we reduce the risk of particles inside this environment? And listen, this is a process. This process is a process of reduction and control, but there are penalties to be paid for all of this stuff, whether we're running systems continually, whether we're opening windows and we're having to run the heat continually, whether the particles are building up from the children themselves. Everything has a benefit and a penalty. So there's no one easy answer. It's just a combination of these different philosophies depending on the room configuration and how it's set up. So let's take, for example, there was a recent article in Spain about, they started opening up their classroom windows a couple months ago, and they immediately ran into this issue of really the children sitting close to the open windows. Over here, for example, let me get my little drawing tool. So the open window would be here, and the students are sitting here. They were getting moisture condensation. These children are freezing. They had to have winter coats on. There was a concern of them getting pneumonia instead of COVID, and it became a real issue that they have been grappling with too. But we want to talk a little bit about opening windows and letting fresh air into the building, because there's a little bit of a misnomer that I want to be clear on here. We can open up windows and it will bring in fresh, more oxygen and displace the CO2, which is an absolute known condition that helps with indoor air quality. But before we get into talking about the indoor air quality and the improvements from opening windows, I want you to understand a little bit about the size of this virus. And to do that, we're going to look at this brittle brush plant. This will only take a minute, but when we take a look at the brittle brush plant, these are optical images through microscopes. And we start taking a look at where the pollen resides on the stamen of the flower. This is to give you an idea of how small the virus actually is. So when we start looking at this this is a scanning electron microscope slide, we start looking at this, we can start to make out that on here is little nodules of pollen. And in the world of particles, pollen is actually a gigantic particle. So when it comes to viruses or even small particles from just general diesel-related soot or outside air, pollen is still a very large particle. When we take a look at these pollen particles, we start to see at 50 microns that we start to get into a realm where they become invisible. Unless they're accumulated in a large quantity, we really don't see them in the air. And it's important to start thinking in terms of everything that we're concerned about is pretty much invisible to the naked eye. Now, as we get smaller, this is 10 microns in size, and this is 5 microns in size. As we get smaller, we see that the virus itself, the COVID virus, generally is about this size in comparison to pollen. It's much, much smaller. And because of that, the way the virus operates is it attaches itself to other particles, and it travels on other particles, and this is how it gets around. We get into some weird effects here with Brownian motion and with the way the particles actually act on their own if they're not attached to it. But for the most part, if they're attached to a larger particle, this is how we're inhaling them, either through expelling someone coughing or sneezing, or through them just attaching to particles themselves. And this is what the MIT and the Harvard studies are predicated on, determining how quickly they can spread. Now, to give you a further idea of the size of the particle, if you look down at this red area here, you can see by the red arrow, where am I here? Here I am. By the red arrow here, you can see that the size of the coronavirus particle is 0.1 to 0.5 microns. Probably not something most people want to remember or can remember, but it's very, very small, considered to a grain of pollen, and very tiny. And so it's something in an invisible realm that we really can't see with respect to the particle size. Now, the Harvard School of Public Health has put out a 5-step guide to checking ventilation rates in classrooms. And the three main things that they talk about is to increase the outdoor air, to use MERV 13 filters wherever possible on the recirculated air. So that would be inside the air conditioning systems, or MERV or HEPA filters inside room air purifiers that are inside the rooms. Now, we have an issue, even with the Harvard School of Public Health, with the increased outside air. And I'll explain that to you. Increased outside air for displacement of CO2 is wonderful. It is really an indoor air quality solution to dilute the air when CO2 levels start to rise. But CO2 levels and particle entrainment in the air are not connected together. There are two separate issues. So I was asked to take a look at, to begin with, this idea of opening the windows and the doors to increase airflow, which is great. Increasing the natural ventilation into a room makes a lot of sense, especially when it comes to rising CO2. The things that you have to realize, though, especially in this picture here in the red dotted line, is that if you open a single window, there really is no air, cross airflow in a single window opening, or even in a double window opening. You're relying on both the wind pressure and the buoyancy of the air to actually help you have air move into or out of the room. In fact, we really run into a big problem with respect to if the wind is blowing from that side of the building, the outside air particles could be much higher than the inside air particles. Just because the outside air has good oxygen to replace the rising CO2 does not mean that it's free from particles. And our concern here is, by opening up these windows without filtering the air coming in through the window, we could be entraining much higher levels of particles into the environment, and those are the particles that the virus likes to ride on. And so that is one of our concerns. Now, whenever we're looking at, if you're looking to set up a classroom and you want to open windows up, cross ventilation is really a critical element to making sure that we're actually flushing through the room itself in some way, either down here or to the right, that we're flushing the particles through and throughout the room itself. So if only opening a window is our only solution, it may not have great benefit. And in fact, that's what the MIT calculation sheet shows, that opening up a single window may only change the air changes in the room from 0 to about 2 air changes per hour, which is, it's not bad, but the problem is that I've done many, many field studies on this type of situation. And what they're not taking into account is the direction the wind is blowing in that day. If the wind is blowing away from the window in this manner here, you won't get any of those air changes. In fact, it'll just be pulling the heat right out of the room. In fact, the heat, because of the second law of thermodynamics, heat will always go from hot to cold. So as soon as you open the window, the heat from the room is going to be going out through through heat convection currents. So even though it seems like a simple solution to open the windows, it really isn't, unless it's a controlled amount. The MIT study also shows opening a window with a fan. And in that particular case, then you would be actually pushing air into the room, but it has to have somewhere to go. Even if you had a fan that was coming into this room here, if the rest of the room is sealed, once it pressurizes, there's really not going to be much more air coming into the room at that point. So the difference in between heating and cooling, outside cold air and inside warm air, that's one effect. The second effect is oxygen and CO2. That's an indoor air quality effect, which no matter what air you bring in, you'll be increasing oxygen to the CO2 level. That's good for general IAQ, but for the virus, bringing in more particles is problematic. And by opening up the windows, we will be bringing in more particles. And the only ways to actually scrub them out of that environment, you can do it through a cross flow, but then and this might end up going into a hallway. So you're putting a concentrated amount of particles into the hallway. Or the most effective way to do it is to stage out air scrubbers inside the room and scrub the air within the room itself. If the air scrubbers are big enough, you may not even need to open up the windows because, quite frankly, most of the schools have enough oxygen in them that the CO2 levels just aren't rising that much. Now, to take a look at this, there's a URL that you all might want to copy down. It's right here. And this is for the portable air cleaner tool that's put out by Harvard. And I think I have a slide here. Yes. And this is available to anybody who wants to use it. So if your mechanical systems, they're saying if your mechanical systems cannot accommodate the high efficiency filtration, or in this case, if you don't have mechanical systems at all, you can use portable air cleaners with HEPA filters. And that's pretty much running across the board with all the research that we've done. That's pretty much one of the recommendations that we recommend. You're going to choose a portable air cleaner with the right dimensions for the classroom size. So when you a certain size, we want to change the air inside that facility, inside that room, a certain number of times per hour, so that we have the ability to capture enough particles to lower the particle load inside the building. And so if you had a large enough HEPA scrubber, it can do it on its own. If you're using smaller scrubbers that may only calculate out to recirculate the air a few times per hour, then you're going to have additional methods of cleaning the air. One of them, I think, has been to open up the windows, which, by the way, could be introducing higher levels of particles, so you're fighting against yourself. Look, one of the big things that we're trying to do here is we're all working to try to reduce the risk to everyone in the building, teachers, students, everyone, all people inside the facility. And it's a tough time. Everybody's learning all at this time. But the big thing that we really want to be careful of is we don't want to put a lot of energy out for something that we're find out a month or two down the road that we're fighting against ourselves. So if opening up a window causes higher levels of particles inside the room, from a virus standpoint, not an indoor air quality standpoint, but from a virus standpoint, that's probably not the best decision to make.
So everyone, Tom, wait 1 second. Everyone take a deep breath. It's okay. We'll be all right. So I know that we've been pushed down our throats from everybody that it's turn on the heat and open the windows, turn on the heat and open the windows. It depends on the situation. And Tom's going to get into it quite a bit more. It depends on the situation, and it depends on if you can't achieve those air changes per hour. There's a lot of really good stuff in this Harvard study, but you need to think of all the pieces that go along with it. And that's where we are going to start to get into the weeds of this from a facilities operations standpoint, to really explain the fundamentals of how to make sure we're making it as safe as possible. So we've made it pretty safe now, but now there's more research available to say we can make it even safer. So I just want everyone to chill out. It's okay. We'll be all right. We're going to get through this together. And I'll turn it back over to Tom.
Thank you, Ken. Sorry about that. Yeah, I should have eased into it, I guess, a little bit more. This Harvard chart allows us to take a look at the size of the room, how tall the ceilings are, what the airflow delivery rate is for the air cleaners, and this is going to vary from room to room. If it's a teacher's lounge compared to a classroom, if there are windows, if there are not windows, how much ventilation is in the school, and then it kind of sets the ideal range, which I believe most of you already know. The ideal ranges of the air changes per hour. 5 to 6 is excellent on the air changes per hour. What we're trying to do is we're trying to scrub the particles out of the air. Now, folks, I want you to know, and the folks on this call who put this together they're amazing people. Jeff and Ken and Maureen, TJ from Belfor. I'm one of the few people in the country that have actually been measuring this kind of stuff real time and real world applications for many years. And so there's a difference between the technical knowledge of what is put together and what actually happens. And I'm going to show you a little bit in a little while. I'm going to try to show you this so you can kind of get it intuitively into your mind, how we measure this stuff and how we can simplify it. We can actually boil this all down to a really simple methodology at the end of this presentation. We'll show you a little bit about that. And so let me see, I hope I can link out to this. Let's see if I can do it. I'm going to link out right now to hopefully, let me get out of this. Will this run? Okay, I'm going to see if I can now launch this. I'm going to share my content here.
All right, we're getting there. While you're doing that, shifting over, I'm going to just answer a quick question that went out there. The discussion of particles, there was a question about particles in outdoor air as the virus links. And it's not that we're concerned about the virus being sucked in from the outside. What Tom is getting at is that the virus attaches itself to a particle, and that's how it moves around the space. So that's why we're putting in MERV 13 filters. That's why we're putting in these little HEPA scrubbers. We're trying to catch as many particles so that way the virus can't latch onto something, spread around, and then be contracted by someone else. And Tom's going to talk about that a little bit more, but hopefully he can pull up this this tool.
I'm trying my best here, as usual, with this Microsoft tool, and it's not coming up. Isn't that wonderful? Okay. I don't know what to do here except to move. Well, I can only explain to you. Let me get back on the presentation then. I'm sorry.
Okay. No, it's okay.
Okay, this tool here it's an amazing tool at this area here, and I'm going to explain to you why. Some of the things that this tool will show you, this is an online tool developed by MIT, and I'll just talk you through it. What it does is it assumes that one person in the room has COVID-19. Then it hands an incredible amount of control data so that you can look at the variables. One of the variables you can look at is just bringing in outside air and what its effect will be, or bringing in outside air with a fan, or bringing in outside scrubbed air, or putting different types of respirators on. Just a different type of respirator can allow the people to stay in the room much longer. I've worked with it quite a bit. It's fairly remarkable. I'm sorry that I don't have a picture of it for you here. I thought I'd be able to link out to it to do a little demo for you. But at the end of the day, the reality of it is that it comes down to, oops, oh, there it is.
Yeah, I just shared my screen to kind of
wonderful.
To kind of walk us through if that helps.
Yeah, could you go to the room specifications?
Sure.
Sure. Now let's just put in a normal room. Let's say 600 square foot room.
Let's leave it 9 because that's a typical classroom size. If that's okay with you.
So if you look, take the mechanical system, scroll down just a little bit so we can see. There's a little text on the right hand side that I want them to see. On the right hand side there. Yeah, scroll down there. See, now this is where it says 25 people could be in the room for 34 hours. So if you click on the filtration system on the left hand, mechanical ventilation, excuse me.
Oh, you want to go? Yeah, that's okay. Mechanical ventilation,
and you put on closed windows, first of all.
Okay.
If you put on closed windows, you'll see that just above that it says there's 0 air changes per hour. So now it's changed it on the right hand side to say 25 people can be in there for 11 hours, right? That's assuming that one person has COVID here.
Okay.
Now, if you click on, you can do the open windows.
Okay.
And on the open windows, you'll see there's an increase of 2 air changes per hour. What I want you to do is take the filtration systems, the one below.
Yep.
And put none. I'm sorry about this. You have to put this on none because I don't want to give out the wrong information. Go back up to the open windows and change it to closed. Okay, so here we are. We have no filtration system running. Recirculation air is moderate, change moderate to none. Okay, refresh your screen, because sometimes I noticed that the calculation sometimes doesn't refresh and reset those. That's just a little glitchy thing on it. Go back,
Okay.
go back and reset the room specifications. Yeah,
900,
sometimes.
900, we have, we're gonna
Yep.
go close windows.
That's
We're
right.
gonna go none.
Right,
And we're gonna go none.
right. And then in the bottom,
And it's gonna show over here 25 people for 11 hours in that space.
okay, now go to the human behavior tab.
Okay.
And on the human behavior tab, you want to talk about talking and whispering. Go from a disposal surgical mask, the one below,
Yeah.
and just go to a face shield.
Okay.
And if you look at, you'll see if you look at the bottom, it should have changed it.
It did. You have, so now you have for 25 people, if they're only wearing face shields,
That's correct.
they can
So you
only
got-
be in that space for 33 minutes.
Now click on that again on the face shield and go to cotton flannel. And you'll see it's 25 people for 76 minutes. Now click on it again and go to disposal surgical mask.
So it seems like most people are wearing the multi-layer cotton now. I think
Yep.
that seems to be the one that most people are wearing. That gets you to 2 hours. And now you're gonna go with an N95.
Now go
Oh,
to
disposable surgical.
That, but go into the disposable surgical mask goes 25 people to 11 hours. That's the difference that the respirator, the face mask will make just by having a different type of face mask.
That's unbelievable.
Yeah, it's actually pretty profound because of its ability to get the respirable particles out of the air. So instead of having to have a bunch of scrubbers in there, if they're wearing good face masks, it has a profound difference on straining out the virus and allowing us to stay inside that environment. Now, if you have, for example, if you click on filtration system and you go to, I think that's MERV 6, but click on that drop down box.
Yep.
And go to, I think, hospital, go to the hospital general surgery, which gives you MERV 13 or 14.
It gives you MERV 14, yep.
Yeah, and then you go change the air changes per hour, which is the closed windows, to mechanical ventilation.
Yep.
And so you'll see that by using this, you can figure out for any room inside the facility what needs to be done. Now, I realize, everybody, that, you know, it's like, well, what are we going to have to do this for each room? Not necessarily. The idea here is to set some standards. For example, there might be standards set for the face coverings. There might be standards set for the inside of the facility. But at the end of the day, in the way I've done this in the past, at the end of the day, this can all, the amount of particles that are in the room can easily be known. They can be measured quite easily. Right. And so I would encourage everyone to get into this and start taking a look at, in your own districts or in your own areas, what the effects of doing something inside your facility might do as a baseline, and follow this MIT model as a starting point. It's a
really, really powerful tool. So what I've done now is I put single layer cotton mask, a standard classroom, mechanical ventilation like a univent heater with a MERV 6 filter. And where most people are going back hybrid right now, say you cut the class size in half, that's 10 people in the classroom for 7 hours. And that's what they're thinking it's not going to eliminate, it's going to reduce. Again, everything we're doing does have some risk associated with it. We're all faced with decisions that are good enough. You know, what's good enough to make everyone as safe as we possibly can?
That's right.
I don't think anyone thinks, yeah, it's a matter of definition and figuring out where it's going from there. But this is a really powerful thing that you can just see. So recirc air, yeah. So let's recirc the air in a moderate. We'll see what happens there. Oh, so now you can tweak with it a little bit. If you can you put in a HEPA filter for this, like a recirc?
The highest HEPA filtration is when you go for the filtration system up to the hospital, okay, or laboratory. I think that.
Yeah.
Right.
Yeah.
Okay.
Now, the only thing, folks, when you start using this, I did notice a couple of times that just make sure it's refreshing. There's some sort of, I think there's a little bug in this, in the sense that I was using it for a while, it was working fine, and then I noticed it wasn't refreshing. So just every once in a while, you might have to hit refresh and put your data back in.
Okay. And let
Now,
me, you want me to turn this back over to you so you can get back into your presentation? All right, let me.
I got it.
You good?
I think so.
Right.
Yep.
There you go. All right, cool.
Wow, what a team, huh?
Yeah.
Now, the complexity of the air conditioning systems is, first of all, if there is mechanical ventilation systems in there, we can utilize those mechanical systems. We can increase the filtration in the outside air, and we can also control the amount of air that's going through there, again, with leaving the fan in the on position. There are lots of buildings that are controlled by third-party control administrators. I don't know how it works there's just so many buildings in your area, but quite often systems are really, because of energy efficiency, systems are almost always shut off at the end of the day. I definitely would say that we would want to consider leaving systems on at least continually during the operational times, but even then, leave the systems just running. You just need the fan running. You don't necessarily need to heat or cool the air to a greater degree after everyone has left the building. So it's scrubbing the air in the building. But again, the increased air dilution can be increased on an air conditioning unit, but it may have a penalty. Now, I want to talk a little bit about psychological considerations too, because these are a profound issue when it comes to these type of situations. So let's just talk in general. If you have mechanical systems that are in there, if the mechanical systems look dirty or they're not clean, that right there is an issue. And a lot of times when we have registers that are dirty or they don't look clean, return registers or supply registers, that really does not necessarily indicate that the system is dirty, believe it or not. A register like you see here on the left-hand side, this register is something called, that you probably don't ever want to remember, but it's something called the Coanda effect. And this Coanda effect is basically the room air, the dust in the room air over a period of time through static electricity, through the air running through it, will actually collect around the register and around the ceiling. It does not mean the system is clean. The only way to know whether the system is actually clean or not is to actually do an assessment of the system. And right now, we're not promoting just cleaning mechanical systems for the sake of cleaning them for the virus. That's not something that we are, and that is the business that we are in. But we are really not promoting just to clean mechanical systems because it'll reduce the risk, because it may not. But from a psychological effect, cleaning these registers is going to have, it really lets everyone know that we're addressing the systems in every possible way. So there's a psychological impact. Another thing I want you to look out for is if you have circulating systems in your area and you have what we call static registers. This is an air conditioning register that blows air in one direction. Try to start thinking about the fact of, like, the guy that's I'm making a guy here, but the asymptomatic person here that not even aware that they may have something, and no respirator, of course, which they should have. But just think about the idea of, okay, air is flowing constantly over this person because this is a fixed register. The fan is running. And so anyone downstream of that person, we have to think in these terms these days of, okay, where am I in relationship to someone else, and where is the air kind of flowing inside this room? Am I constantly being subjected? And this came out of the China study, the COVID China study, that showed that people in a restaurant that were 2 tables and downstream from the air conditioning vents were actually all subjected and became infected with the COVID because of the way that the air conditioning vents were configured. And I know that a lot of your schools don't have these, but for those that do have these, there is something that can actually be done on those, because there are different types of registers. This is one type. It's a strict directional airflow. This one is what's called the diffused register. You may or may not have them. You can tell them because it has all these little thousands of perforated holes in it. And what it does is it diffuses the air and it allows the air to mix in a more chaotic fashion instead of a linear fashion into the room. And they lower the risk. So there is this question of, well, if we did have these type of registers, Tom, is there anything that could be done to those low cost that could lower the risk? And the answer is yes. What we've done in some cases, like in nursing homes, medical facilities, and other areas, is we've gone in over the registers and we've actually put a filter media, not a high density, but a lower filter media. We're not filtering the air here, we're diffusing it. And we put the filter media over the registers. So in here, you can see, in this area here, you can see that the register is now being covered. And the filter media itself is something that just covers over the register. And we clearly communicate to everyone, look, we're not trying to filter anything out here. We're using a low density media. You can fool around with this, but we communicate to all the staff very clearly that the filter media's primary function is to diffuse the air coming in from those types of registers. So that's something that you can put into your battle chest as well if you have those type of registers inside your facility. Now, I want to talk about air dilution. I started out by telling you that, yes, we can bring in a lot more outside air. And outside air, when we talk about bringing in outside air, and it's most of academia really will tell you bringing in outside air is good for indoor air quality. And that's true. When it's brought through the air conditioning unit or air conditioning system, outside air is great because it's going to immediately, it comes in and hits a filter bank here. So the air is actually filtered as soon as it's brought into the system. Now people say, well, wait a minute, Tom. You know, there's lots of people saying if you have an outdoor dining area, it's much safer than being on the inside. What about that? And that is because there's a constant air flow movement outside. Is air coming from the left to the right to the left, up and down? It's moving continually and exchanging the particles that are around you. That's the big difference. Again, there's a separation between oxygen and CO2, which is great, more oxygen, less CO2, and then the amount of particles that are in the air, or we'll just call them virus-carrying particles. On an air conditioning system, we can actually upgrade the filtration and increase the amount of filtration here. Well, how do we know, Tom, that we're reducing the particles inside the building? That's the big holy grail, and that's the easiest answer of all. We can measure it. It's very easy to measure the amount of particles that are in the building, whether they're rising or lowering. Some of these air conditioning systems, I don't know if a lot of you have started working in your areas to find out, many of them on older systems will be kind of shut or closed or haven't been used in years. Many years ago, a lot of these were shut down for energy efficiency, just to save energy. If it's too cold out, the heat's going to run constantly by bringing in colder air, and that's another penalty of opening these up. And the penalty can be pretty steep in some cases. You're bringing in colder air, you're intentionally bringing in colder air, you're filtering it, and then you have to reheat it to make the area comfortable. And it's the same penalty with opening windows, by the way. And so if we open the windows inside here, one of the first things I think would be a good idea is if we're going to open windows, which in some cases might be great, we try to filter it in some way. And there's filter media that can just be put over the windows in some way. This would require a little bit further discussion how to do this in a quick and meaningful way. But opening up the window can create a bigger problem. You have to consider it on a case-by-case basis. I want you to remember the second law of thermodynamics, right? This is physics here. The second law of thermodynamics is heat always goes from hot to cold. So if you're warm inside and you open up a window and there is no air moving outside, it's a dead air day, you're going to have air movement out of the windows, not in. So because of the second law of thermodynamics, things will be moving out. Now, if it's a sealed classroom and there's no doors open, there's going to be some temperature movement, which carries a little bit of air currents with it, there'll be temperature movement for sure. But that's not the way life really works. What happens is from time to time, you have air blowing in, you have air changing directions, and depending on what side of the building I've had buildings set up where we had to have absolute 100% control on the rooms as far as pressurization is concerned, and the air would change direction and it would positively pressurize a room way beyond 10 times higher than we thought that we can control beyond. It is a variable, is what we're saying here. It is a variable that's really very difficult to control unless you're setting up fans inside here. So it's not a one-stop works perfect measure. It can be done, and it may need to be cases, but we need to know the implications of it. So on dilution, the dilution of the air is used to primarily control the level of CO2 with increased oxygen. So a lot of people think that the level of CO2 is an indicator. They intuitively think that the particle control is coupled with the CO2. It's not. CO2 level, lots of kids in the room, and there's less children, there's going to be less students in rooms now. But if you put a bunch of people in a sealed box, the CO2 level goes up. There's no doubt about it. Introducing more oxygen brings the CO2 level down, as long as you have some sort of cross ventilation where you can get the CO2 out. That does not correlate directly to the particle concentrations. You can be bringing in great oxygen, but with high levels of particles. For example, if the wind's blowing through the trees and the leaves are out there and it's rustling, I'm in Florida right now, so I did grow up in New York, but probably most of the leaves are down now. But depending on the outside conditions might be wonderful and have very low particles, or it could be very high. The outside air does not necessarily mean that it's cleaner air with respect to particles. So the EPA also has really good information on this now, quite frankly. It says avoid, one of the things that they have on their site, and the link is on the bottom and we can distribute this, is ventilation with outdoor air when outdoor air pollution is high or when it makes your home too cold or humid. So they're recognizing, they are recognizing and validating what I'm telling you, which is outdoor pollution can be very high and you're introducing that air into the indoor environment. And for the most part, the only problem that this causes us is because the virus is acting differently from an indoor air quality standpoint. The virus is looking for particles to attach itself to. So we want to reduce particles whenever possible. They have a Check Air Now information deal on their site. In situations where wildfires are concerned, follow local advisories. And they're also talking about what's going on in California as well. So something like this is my biggest concern. It really is one of the larger concerns that I have about opening windows. I've had several projects where, and I know that this is controlled, this is trying to be controlled, and having automobiles standing and running in the wintertime is something that's frowned upon, but you have the school buses coming in, you have all the vehicles coming in, you have windows open in the morning, and you have all this diesel particulate, gas particulate, and it is a massive amount when you start measuring it. That's actually entering into the school that we have to scrub out. Those are particles that could potentially, the virus can attach itself to. And so this is the big concern about opening up windows and being aware of what we're doing. If you don't have this issue, then your risk is lower to opening up the windows, and it just needs to be taken into account for each school and how the schools operate and what they're doing. However, if you do have lots of particles, or if you're near a highway, or if there's lots of trees around, the particles generally are going to be high. And the second part of it is the students themselves. When you're measuring when you can measure very easily, we could measure invisible particles on the indoor environment. We use a meter called the laser particle meter. It measures invisible, getting to be very popular now. And so you can stand inside a room, and when everyone's coming in and taking off their coats and whatnot, and they have all the dander from the cats and the dogs at home, and they have, everything that's been on their jackets and on their clothes, and then them themselves. And you'll see the particle rise dramatically when they first show up, and then as the day goes by, depending on the setup of the classroom, it'll start to drop down, and then it'll raise back up again with activity. So this also generates particles. So I think a lot of you are getting the idea now is that a main part of the training that Jeff and I are trying to do here is to get everyone to understand that we're more concerned with particles and the control of particles than we are with CO2 and oxygen with specifics. I
think people are getting it, Tom, because the message board has been extremely active right now. So I wanted to jump in here for a second. Just looking at the relationship with particles versus the outdoor air, and how once the particles do get in there, because if the virus is in the space, how do we get them out? And you kind of touched about that. But there was one question about duration of time in the classrooms as it relates to air changes per hour and particles. So, like, for instance, if it's an 8-hour day and kids are changing classes in that space, it's a high school environment, does that 8 hours, does that clock start ticking the minute the buses show up in the morning? Or is there a segue break in between? Say the space is unoccupied for 10 or 15 minutes. Where does that clock start ticking again?
That's a great question that I do not have the answer to yet. It was asked to me by my mentor as well when we were studying the MIT, and I haven't dug into it enough yet. But we don't know what the reset time is for a room.
Would it be fair? I'll let Jeff jump in.
Yeah, I mean, you do know from, say, 6 air changes per hour, for example, is every 10 minutes, you've scrubbed all of the air within that room. Now, do you get a complete reduction to 0, for example, in that 10 minutes? The answer is no. But every 10 minutes, you are completely circulating the air within that room. Across the filter bed. So each iteration, every time you go across that filter bed, you do get a chance to clean that air. So if you have like a lunch break, for example, and 30 minutes goes by and then the group comes back in, you have restored that air to at least a measurable reduction. And so I do believe the clock is really restarting by giving that time increment in between those air changes.
Yes, and that it actually, what you're doing is you're restoring it to its lowest possible particle load at that point. So what again, this is like a rubber band. The machine is trying to keep up with the particle load, and if it's large enough, it can easily keep up with the particle load to a certain degree. And it's actually fairly profound. These machines, these HEPA scrubbing machines, are fairly amazing. When they're sized appropriately, they will keep the particles very, very low. I'm going to show everybody that in a second about a project that we've done recently.
And just so folks know, in the interest of time, we might run a little bit long, so hopefully people can stick around. If you can't stick around, the recording and the PowerPoints will be made available, so don't worry about that. Because I do want to add one quick component, because this has been something that's been stirring around from a cleaning standpoint. And I know we're talking about HVAC, particle load that's on our floors. People are talking about, oh, do we need to disinfect the floor surface? What do we need to do? And the guidance, is still the same guidance that it's always been. Vacuum the floors with a HEPA vacuum. Pick up as much particles as you can. Don't go in there with the dust broom, start sweeping around like we used to in the old days, and just go out in the hallway and shake it out to get that dust into one big pile of dust on the floor. Get in there with a HEPA vac, vacuum the floor, you'll be good. And it's reducing that part in the space, which is going to help not allow that virus to attach itself to a larger particle, and that's how it's moving around the space. So I just wanted to kind of add that in there as part of this discussion.
Yes, and let me just add to that for a second. You can put your mind to rest about some of the stuff on the floor, and here's the reason why. Any particle that's dropped to the floor is too heavy to be in suspension. So the HEPA vacuum is critical, because as you're removing it from the floor, you want to capture it and make sure it doesn't get resuspended in any way or emascerated in the vacuum In other words, if it's heavy on the floor, it gets picked up. You don't want to chop it up further, make it smaller, so then it becomes suspended. So absolutely the best thing to do is to have to vacuum up the floor. But remember, if I have, sometimes it's best in particles to think in terms of seeds. If I have a bowl full of mustard seeds, and I just literally take a handful of them and throw them up in the air, all of them will drop to the floor, because in that case, the weight of the particles just drops out of suspension. We are not really concerned about those particles. The particles that we're concerned about are the invisible ones that you cannot see. So, I mean, not saying that good housekeeping isn't absolutely essential here. You want all surfaces wiped down. That's a given in this presentation, that's all being done. But the invisible particles that we're bringing in from outside, you can't see these particles. They can only be measured with devices. I hope I didn't contradict anything you just said, Ken.
No, you actually added to it, and it makes perfect sense. So thank you for that.
So I know time is critical here. So let me just show you a few more slides. This is what we call computational fluid dynamics, fancy name for we can see what air does inside a building. And nowadays with computers, we can actually calculate and see how air movement. This isn't anything we're proposing for the schools or anything like that. It is for to get an understanding of what really happens inside an environment. In that lower right picture here, you can see that really the particles that are in the air, you're either removing them or they can get everywhere. So the whole process of this becomes, let's just remove as much as we possibly can to lower the risk. Depending on how the room is configured, though, like up in this area, the particles might be much, much less than in the area where they're actually being initially entered into the environment. And of course, in office environments, open cubicle areas have a higher rate of particles than lower areas. And in this particular case, if there are sealed offices, let's just say that this was a teacher's lounge here. If this was a teacher's lounge with one door coming in and maybe a register or two in here, when everyone is in here, an air scrubber, a HEPA scrubber is really kind of critical in this environment, because there's really no way for the particles, the high suspended particles, to get out unless there's a mechanical system moving the air in here, or there's a way of just generating air to be moved through a scrubber in and out. So areas like a lounge or something like that have to be considered differently. But if you take a look at, if you had an office environment in the school where the office did have one supply duct coming in and one door, well, this becomes positively pressurized, this office. And so if there's good filters inside the mechanical system, what's happening in here is the positive pressure is constantly moving air out these doors. So this is a much safer environment. Plus, usually these single offices, the risk is much lower because there's only one or two people inside the office to begin with. And then again, we have respirators. And then we have an open cubicle environment, which is just like a open school environment in many cases. And those areas are best served by placing scrubbers in the general areas to reduce the overall burden. So that's kind of the only problem that we have here is with the scrubbers, and it's not really a problem, but you just have to select scrubbers that are noisy. The decibel issue can be a problem. But how do we validate? Okay, with all the complications that we just talked about, Tom, what are we supposed to do? It's actually a very easy way to validate this. So we have a device. It's called the laser particle meter. I don't know if you've ever heard of these, but it's becoming a daily tool. And the laser particle meter measures the amount of particles that are in the air. This particular one has 6 channels on it. 6 channels meaning 6 different size particles. 2.0 is the one that the APA talks about a lot, 2.5. But 10, they say 10 is about the smallest particle a visible eye can see, and then everything else here is really essentially invisible. So you're measuring invisible particles. And in this particular project, what we look at is we look at these 0.3 particles, because this is the one, these are the small particles that the HEPA scrubbers are designed to remove. But any of these particles from 1 to 3 are particles that the virus can attach to. In this particular case, on this day, the outside air had 3.3 particles in it per cubic meter of air. So for every cubic meter, or basically cubic yard, for those of us who aren't that fond of metric, but for every cubic meter of air, the sample comes in through this device and it says, oh, we're extrapolating this out and we're going to tell you that you have 3.3 million particles at 0.3 microns. Now, some of you, I hope, are shocked that that is even possible to have 3.3 million particles at 0.3 microns, but that's not an abnormal number for outside air. But with a well-ventilated building, and this particular building was concerned about, this was a research lab, but this building, with the filtration that they had inside their units, we took readings inside, and in the first floor cubicles, you can see that the inside reading was 330,000 at 0.3 microns, which meant that the air was 10 times cleaner than the outside air. Well, how did we achieve that? What I'm trying to tell you is this can be measured. You with all the things that you may or may not want to do, opening windows, closing windows, upgrading filters, put small scrubbers, put 2 scrubbers, everything can come down to just taking a measurement inside and saying, look, we're 10 times lower than the outside air. We've lowered the risk. It's not perfect, but we are lowering the risk. We're not increasing the risk. And that's the way you have to kind of look at this. You know, if you had 3 million particles, yes, sir.
Tom, that looks like a pretty fancy tool. Is that pretty expensive? Can I do that on the cheap?
I'm going to show you. I actually took the time to show you that, and this is another area of the facility. This is 717,000. Now, this is the outside air that's taking in the air to the air conditioning unit. And right at the air conditioning unit, it's pulling it in at 3 million, but the filters are filtering it out. Our company as well is looking heavily into getting lower cost. These meters can be very expensive. They range from $1,000 to $4,000, but these 2 meters right here on Amazon, they have to be able to read 0.3 microns. So that's the only thing that you really have to make sure that they read in 0.3 microns. But I haven't ordered one of these yet, but I am going to be ordering one this week to compare it against our other meters. But these meters, I found them. This one is $232. I'm not speaking for how well it is, and this one's $639, maybe a little bit better. I don't know. The point of it is that when you use these meters, the main thing that you want to do is compare it to the outside air. Now, I just want to point out one thing to everybody in this little particle lesson. In the same day, this can be going 3.3 million, and in 2 hours you can go back out and it could be at 10 million. And 10 million would not be a terribly offensive number to see. You would absolutely say, oh, wait a minute, all the cars are showing up. Now that the cars are showing up in here, we can see that all the diesel particulate in the air is causing this elevated level. You'll see it. There's nothing to guess about at all. So I want you to consider thinking about doing something like this. At the end of the day, whether you open windows or close windows, you upgrade filtration, you don't. Whatever you do, at least you may want to have several of these distributed. So in the event someone's concerned about a room or not concerned about a room, we can absolutely definitively tell what's going on inside that room from a particle standpoint, not from a CO2 standpoint, but from a particle standpoint, to see if we're controlling the particles.
And again, this kind of goes a little bit into a deeper dive than what DESE and what Harvard and what everyone has been saying up to now. And in addition to the Mass Teachers Association, we've been so focused on air changes per hour and focused on CO2 levels, you know, to the point where everyone's recommending we install CO2 monitors in each classroom so teachers can track it. This is additional information that's going to help you provide an extra layer of security and really get to the root of the problem. And it's how the virus attaches to the particulate matter that's in the space, and that's how it moves around. So if we can track the particulate level and show that we have a reduction in our spaces, This is just another tool in your tool bag. Much like you have thermal scanners, you know, you have your temperature sensors, you have all that stuff. It's another tool that's going to allow you to better understand how your building is working.
And Ken, some of these meters have built-in CO2 on them as well. Now they'll be a little bit more expensive, but for that matter, you know, think in terms of someone's concerned about the students in a classroom. You have a definitive number, and it's an absolute that you can give back the information on. You know, there's just no doubt about it. You're not guessing, no one's guessing at all at this point.
Yeah, and Tom and I and Jeff had spoken earlier that this ties in with the importance of knowing what's coming into your building. You have to take outside measurements before you take your inside measurements. You need to have both levels of information. Otherwise, you don't have a baseline to compare against. And like Tom had mentioned, the outdoor air quality changes drastically in a very short time. In addition to the parts per million for particulate level, it's also your CO2 levels. Your CO2 levels do rise and fall just like the particulate level does. So having that understanding of how your building responds to outside, I think, is a critical part.
It all depends on where the school is located. If it's next to an industry, if it's next to highways, if it varies from one location. There's no cookie cutter on this.
Right. And John Nelson just posted a link to Granger for a particulate counter that's up on Granger as well. Thanks, John.
Ah, that's wonderful. Yeah. So I do want to mention, and I'm going to lump this all together with respect to, you know, lots of people are talking about, you know, UV lighting, bipolar ionization, electrostatic precipitators, hydroxyl radical generators, ozone generators. And although there's a tremendous interest, and these things do work in standalone room air purifiers, for example, that have supplemental UV in there with the HEPA filtration in it. You know, there's a report. I didn't put the link here, but that's the name of the report right there on top. A review of enhancements to HVAC systems marketed to address COVID-19 and improve overall air quality. It's a very good report. It discusses the positives and negatives of all of these things. UV lights, I'll make my short version of this. UV lights do work. Direct exposure to the coil will keep a coil clean. Whether they actually will inactivate the virus on a single pass requires some pretty trick engineering understandings of airflow rates, and you would really have to, it gets a little bit complicated to know the flow rate of a mechanical system. You really have to start off, frankly, if you're installing these things in a mechanical system and the mechanical units haven't been cleaned, that's something that I frown upon. So no, in other words, just installing UV lights without actually restoring and cleaning an older unit, it just doesn't, it really doesn't make a lot of sense. However, they do have a positive effect. There's no doubt about it. Some of them can produce ozone, which can be an irritant. Some of them don't. But at the end of the day, when all else is said and done, with a limited budget of money, I prefer, frankly, to see as much money put into air scrubbers and reducing the particles, the virus-carrying particles inside the environment whenever possible. And so it does come down to, in a perfect world, of unlimited budgets, let's do it all. But in this particular case, I prefer to see most of the investment go into either the scrubbers or measuring the particles with laser particle meters to know what's going on. Heck, you might turn on the laser particle meter and there's not a problem at all. It might be lower than the outside. It all depends. And finally, even though this is Belfor, I represent a subsidiary of Belfor, which is called Dux, and basically we spend our life restoring and cleaning mechanical systems and then upgrading the filtration and trying to get systems cleaner and running cleaner with higher filtration and MERV filtration. I know many of you have read about increasing the filters inside these units. I am just getting access to a brand new type of filter out there that is very, very high level filter with very low pressure drop. And we're going to be at, which is close to HEPA, that you could put on almost any system, but nevertheless, most systems can endure up to about a MERV 12, MERV 13 filter. There is a little bit of an energy penalty on it, but it does have a measurable, profound difference on the air quality if you upgrade your filtration, make sure the filter bank is sealed tightly, and you could measure the reduction by leaving the fans on. And one thing about filters that I want you to understand is that with HEPA filters and many filters on the marketplace, they filter out essentially by straining, okay? So in other words, if you're trying to filter out mosquitoes and you have a chain link fence or even chicken wire, it's not going to cut it, right? But there's nothing that strains out the virus. The virus is too small to fit through. The virus will pass through virtually any filter, the virus particle itself. But the virus particle travels on other particles, which is the reason why respirators work so well. So when we're talking about using a HEPA filter, we're not screening out the virus just itself. It's too small. It would actually, much of it would pass through if it was just the virus. But because of it's traveling on other particles, that's why the higher MERV reading captures more dust, makes a cleaner environment, and captures more particles. We do get to a point, by the way, on some of these filtration devices, like this one here, the electronic precipitator. These electrostatic precipitators are actually, they generate a corona. They generate a high corona and they have a receptor plate. Too much information for most of us to know. But what happens is it positively charges all particles passing through, and then they get attracted to the plates. All of these things require maintenance, though. Even the UV lights. I mean, it can be a big investment, and they're not going to last more than 16 months. The actual effectiveness of them. So, everything here has an upside and a downside. We do really want to be careful of using any ozone or ozone generating devices, because that's an irritant on the indoor environment. Now, there are I know one of the folks in my company bought this for their child's classroom. This is a HEPA scrubber. It's hospital grade, no ozone, UVC. There's a UVC bulb inside here. This is very expensive. It's $8,000 for this device. So I put this as the high end. It looks like R2D2 on steroids, quite frankly. But these devices, these Honeywell devices, these move 250 CFM of air. You might need 2 of them in a classroom. But these are actually very good for scrubbing the air as well. Again, and they can last a fairly long time. Or you can go with a commercial scrubber. I have a facility that I have people meeting in regularly. And I've been doing this for months now, more than months. I've been doing it since March. And I have scrubbers run inside my environment, and I measure the particles inside there. And we run the scrubbers, believe it or not, the only time when meetings are occurring, we have meetings that occur at different times. We actually either turn this down to its lowest speed, and in some cases we'll turn it off for the meeting, but then they're always put back on to scrub the air between meetings or during the meetings. Generally, the one that I have that's the variable speed, we leave it on low speed the whole time and then ramp it back up. But we're controlling the particles well below the background, and that's the most we can really do. We can just offer that to the folks coming there and wear respirators. I mean, no one's allowed in the facility without a respirator. If they don't, wear a respirator, then they have to, they can't attend. Or in cases of the school, they have to do the homeschooling. So
and something just to remind people about buying the HEPA scrubbers, and I mean those are highly recommended by Harvard, highly recommended by DESE. I think a lot of districts have purchased them. These require maintenance, so hopefully these will come out of circulation after the COVID issues go away, and we can put them in a storage container potentially for the next pandemic. But just make sure that you're doing your proper maintenance on them. They need filters. They need to be cleaned. Don't go and store them with dirty filters in them. Be smart about it. Do you know how many you have? Can you get new filter media? all that kind of stuff. There's a cost implication, and these do have a life cycle. The Honeywell unit, while the price point's cheap, I don't know if it can handle, the stressors of being moved around during summer cleaning for the next 5 years in a middle school
No.
environment.
I-
So it's almost a
like these
consumable.
I like the more of the commercial machines, and in the event, Ken, I know we had discussed this a little bit too. The thing about this machine is, in the event the pandemic's over and we have tons of these actually can go be they can actually be sold back off to the restoration industry for usage for mold remediation and other stuff. So there's also that possibility as well.
Okay.
It's like, okay, look, now we have a couple of hundred of these machines. We don't need them now. What are we going to do with them? So I like the semi-commercial machines. This is actually a small, it may look big, but it's only I think it's only like 18 by 18, this particular unit.
Well, and if you look at the price point on that unit's doing twice as much for twice the price. So if you needed two in a room, one of these might be sufficient compared to two Honeywells.
I have one of these. I have this exact machine in a room that's about, I'd say, 30 by 40, and it's scrubbing. It's controlling the air. And it's probably a bigger room than it should be in, but it's still doing it.
Great, thank you.
Okay, so then at the end of the day, it really is a good idea to at least have an assessment of what your air conditioning systems look like. And look, I'm not going to get into, look, are the systems already dirty? They're not dirty. Many systems, over a period of time become dirty. That's just nature of the beast. What I would encourage everyone to do is absolutely check to make sure that the filter banks are intact, that the high level of filtration is in place, and check the outside air dampers to see what position they're in. And it's going to require work. That's going to require work to make sure, and just have a real understanding of where these air conditioning or heating systems are at. Jeff, do you want to talk about
Sure.
a little bit about this?
So one of the concerns we have, especially with everyone opening windows, is how that's going to impact individual classrooms. And as we recognize, say, a teacher is the one who opens the window up, and at the end of the day, perhaps they forget to close it up. It's going to be important to walk these buildings on a regular basis, especially on the evenings or on, say, the Friday right before the long weekend, to make sure that all these windows are being closed up and things are being buttoned up, if you will, for the lower temperatures. The other part of this is considering running your temperatures a little bit warmer than you might have, especially in considering that somebody's going to be opening up windows. Open up your cabinet doors underneath your sinks. That lets that hot air get underneath there, so your plumbing gets a chance to warm up. If you have those doors closed, the warm air doesn't get underneath there. So all of these are good as far as being proactive on your buildings, recognizing that there is going to be individuals who are going to want to open up windows and ventilate these buildings. So you're going to have to be more proactive in your freeze protection efforts because of that extra person, if you will, who's probably opening a window and may forget to do that. So I think that's the basic take home on this preventative maintenance, is that things are going to be slightly different this winter, perhaps, than previous winters. And I think that's probably enough of the pointers off of this. I believe, Ken, you've circulated this to some of your folks. So
yeah,
so
I'll circulate it. Oh, sorry, feedback. I'll circulate it back out again, just as a reminder. The reason we're mostly concerned about it, and Maya's on the call as well, and they're concerned about it, is a lot of folks have put their systems in bypass or mechanically forced open that we haven't had to do historically. So what we're seeing is that, I mean, that's just opening a potential risk that, okay, the system's in bypass, we're bringing in more but our building doesn't have glycol in the heating system. So are we going to start popping coils?
Yeah, I mean,
so it's just making everyone aware that we're vulnerable. So double check, triple check, quadruple check, and make sure you're putting some steps in place to avoid catastrophic failures.
Yeah, just be hyper vigilant. This will be the first winter where conditions will be different than other previous winters. I mean, there's just no doubt about it.
So to boil it down, in summary, number one, have the students wear a good mask. Use the MIT tool to look at the differences. If we fundamentally absorb and understand the differences, it gives us more validity when we're promoting these policies. Of course, limit the number of people and the exposure time whenever possible. And then optimize the engineered ventilation, in accordance with the EPA, and optimize the filtration and circulation. These are all strategies to help both reduce the particle load and increase ventilation inside the system. And whenever in doubt, at least have access to somewhere in the system to a particle meter, because that really ends all speculation on what's going on inside the room. You could measure the particles. It's invisible particles. It's very hard for all of us to understand that when we're looking at someone 6 feet away from us, that there's potentially, for every cubic meter of air, there's potentially 3 million particles floating between. So it's like, it doesn't even make sense. I can see you perfectly. How can there be particles in the air? Well, there are. It's just the way it works. That's why on very, very cold, crisp days, when the particles are low, things just seem to be a lot sharper. Things look sharper, right? So when we're outside, any viral particles released are likely to be carried away by wind currents. I wanted to make that point as well, because people are tying the bring outside air into the inside, because outside seating is good, risk is lower. Risk should be lower if we bring outside air in. Well, that's because of the wind currents carry away those particles, and they're constantly changing. They're able to freely move. When you're trying to open a window into a room, you usually have an enclosed room. And if you have air passing through the room, then you're moving those particles to another part of the building, unless you're driving them out. And that, believe it or not, that is actually something that we had considered, which is if you put a fan in the window and faced it out and then opened up the door of the classroom, you'd be pulling air from the hallways through the classroom and out, which would be good, but you're really going to be ejecting a lot of heat out of that classroom. And so that's a very high penalty on energy. And as a result, the caution for people to stay 6 feet apart may not be enough if you haven't put some of these items in place. So we have both the Harvard School and the MIT links in this presentation, so that anyone who wants the presentation can pick up the links from here or use those tools. I think I really prefer the MIT one. It's easier to use. There is an article from Spain about schools that face the exact same dilemma. It might be interesting for you to read this article about the leaving the windows open and the problems with cold and ventilation systems and all that they're running into. And we have wonderful support people on with us, Maureen and Thomas. Maureen represents Rimkus and Thomas represents Belfor. And we have, for any questions that you have with respect to this stuff, they're in your area. They represent the Boston area as well. And so they'd be the local contacts to get with, the folks that brought me in and Jeff in as well. So do you have any questions that you have out there lying out there right now, Ken?
It looks like any questions we had on the question board have been answered and have been. If something does come up, we can certainly reach out to TJ and to Maureen to get in contact with either you, Tom, or with Jeff. I just would like to say on behalf of the MFAA, I really appreciate the time and energy that went into you guys putting together this presentation. It was really, really powerful information, gave some great resources, and continued to extend the conversation as to some different options to continually improving our chances of combating this pandemic. Shifting the conversation from CO2 to tracking particulate level makes sense from a facility standpoint, but that's a hard thing to translate into a layperson standpoint. So yes. I think it's shifting the conversation a little bit. I'm going to be working with DESE on this as well. We had I think there's a lot of stories changing, a lot of direction changing. We're used to that, but I think this does give us another layer of protection that's certainly going to help reduce and provide a safer learning environment for both our students and our staff. And that's a big thing. It's the kids can fight this off a little bit better than us grown-ups can. So it's trying to figure out how to minimize or reduce that risk, because we're not going to be able to eliminate it. That's for sure. So thank you again. I know we ran a little bit late, so thank you everyone that was able to stick around. What we're going to do is we are going to share this PowerPoint and share the video. Once we get the video squared away and cleaned up, I will post it on our YouTube page and we'll send that out to folks. And again, thank you everyone for all your time. Stay safe and happy holidays if I don't talk to you before then. Take care.
Thank you.
Thanks.